Hello, welcome to Subspace Mechanics. This is the first lecture of the series, and so I'll have to apologize. There are very few equations in this lecture, but I hope you stick around anyway, get some context going in terms of what the rest of the series will be about. The name of the series here, Subspace Mechanics. And let's get started by talking a little bit about some of the motivation behind studying it. Of course, most of you are probably here because you want to build spaceships. And a very particular kind of spaceship, one which can travel superluminally. And of course, you'll need some subspace mechanics to do this. And I should point out while we're discussing it that it is not the case that we absolutely need superluminal travel to outsurvive our star. It's possible to survive in other ways. There's panspermia, and there's even the survival of cultural aspects of humanity, which could be possible with subluminal travel. This has been explored by many sci-fi authors. There's some other sci-fi concepts that come up with subspace mechanics. Superluminal travel, the most popular design is the Alcubierre warp drive. There are other designs, so you need to have some idea what's going on in the subspace to do these things. Another thing you will need this for is electrogravitics. If you're going to have any kind of novel propulsion based on electrogravitics or novel artificial gravity, you'll need to have some knowledge of subspace mechanics. And there's some more reasonable reasons to study this stuff. One is to get just an understanding of fundamental physics and field theory, by which I mean electromagnetism, quantum mechanics, general relativity, especially those three. And associative mechanics is, in a way, it's sort of a unifying force in understanding these different fields. And the sort of canonical example which we follow is that of kinetic theory of gases. And in the kinetic theory of gases, we have some fields. In gas, there's a temperature. At every position in time has a temperature. That's a field, a scalar field. There's a pressure, another scalar field, although pressure can be more complicated. There's a density of gas at every point in time. And there's a bulk flow, a wind speed, if you will, at every flow speed at every point in time. That's a vector. There's pressure tensors we can define. There's lots of different fields we can define in kinetic theory of gases. And in the kinetic theory of gases, we describe these all as being arising from a kinetic description of molecules of gas moving about molecules. Real simple molecules with position and velocity at different times, and that's basically it. So we have a distribution function of these molecules, what's their density in certain positions and in phase space at certain speeds and at certain times, and from this we can create a whole theory of physics based on the calculations of the mechanics of these gases. Now, this is might seem totally normal to you today, but when Boltzmann was describing it, people thought this was crazy, and they said, look, we can already do all the physics we need with simple things like the ideal gas law and empirical laws that describe these fields, and there's no need to talk about any kind of molecules because we can just do empirical physics with these fields. And in fact, that's true. If you're building a refrigerator, for example, today, you're probably not going to use the kinetic theory of gases. You're probably going to use empirical laws, like such as this ideal gas law, to do the engineering required. But for this lecture series, we're going to be using this approach of describing things from their fundamental constituents. This is also a atomic theory from Democritus, Leucippus. So you might be curious if I'm about to describe a theory of everything to you. And the answer is mostly no. And it's worth taking a couple minutes to say why the literal interpretation of a theory of everything is ridiculous. There's, for one thing, is that as the sphere of knowledge grows, so here's our sphere of knowledge, some radius r, and grows out, gets bigger, we learn more things. The surface area of the unknown along this edge here grows with it. So the more you know, the more you know you don't know. The more questions there are, as every child is familiar with. There's more things to ask why about. There's more unknowns. So the idea of a theory of everything is absurd from that standpoint. Also absurd because theories have domains. Sorry, you just do. They have theories are for using, for modeling things, and why would you want to use the same theory to model an ant colony as you would to model a neutron star? It's unclear that you would want to have one theory for everything. And finally, well, not finally, but where we will stop is to point out that there will always be multiple models consistent with observation. In other words, there's no way that there could ever be one theory that will describe any system. It's just not possible. You can come up with this just by the nature of our observation platform, our bodies, and seeing how we observe the world. There's always going to be multiple models consistent with our observations. So we can say we like one more than another for certain reasons, but there's no theory of everything. There's always going to be multiple theories, and they'll never cover everything. But however, we will be in somehow doing some unification, and sometimes people refer to this as pursuing a theory of everything. And as a catchphrase, why not call it a theory of everything? Then we could maybe go on Kurt Mungo. Props to his podcast. And just because the literal interpretation of theory of everything is absurd doesn't mean we can't use this phrase, this coin of phrase, to help market subspace mechanics. So let's talk about what is subspace. Let's check on my OBS here. Yeah, we're still good. What is subspace? So quite simply, subspace is another coordinate system that is not our ordinary space, but which we need to describe the constituents that make space-time. So in other words, if we go back to a very old and interesting article from Lee Smolin from Scientific American in the late 90s, I believe, it was called Atoms of Space. And we are pursuing this approach to describing space-time. And atoms of space have to live in some space. If these behavior of these atoms is what gives rise to our notions of distance and time, then what distance and time do these atoms live in? Now, we're going to use a word borrowing from Frank Mino called gyrons, and we're going to refer to atoms of space as gyrons. And subspace there's no reason that it has to look like our own space, other than that helps us in the simplest possible way, intuitively. But the enterprising student will, of course, look at all other types of models in different dimensions. Any kind of model will potentially produce our fields. So what are we trying to produce? What are we trying to do here? Well, fields. What are the fields we are looking for? We're looking for an electric field. We're looking for a magnetic field. These are physical things. They exist in a vacuum and exist in places with mass density as well. There's a metric tensor. There's a metric tensor, G mu nu, and this describes the gravity field, if you will. These are fields, and that exists also where there's no massive material. This is in a vacuum. We have all these things, and then we have some things which are not vacuum. For example, we have a electron wave function describing electron density. We have muon density, tauon density, and some other quarks and antiparticle. They all have a wave function, and so all these fields describe the world around us. And they can be written in other ways, of course. E and B, we can write it as an electric field, an electric tension, Spannung. We can use a magnetic vector potential, get the same information. Of course, we can, G mu nu is related to the stress energy tensor by the Einstein equation. We can write these things with different variables. But in general, these things describe everything around us. And the electric field here is really a big one, because that's what builds our space-time. It's what keeps my body from falling to the center of the Earth right now. It's the electric field forces between the atoms of this floor that prevent the atoms in my body from going right through. If we look at this electric field, it might be, and we're talking about a theory of everything, and it's a fun diversion to consider something I'm going to call a God API, which is a function we can call, which returns an electric field at any position in geocentric coordinates and time. And this is a theory of everything, really, because this will tell us everything that ever was and will be. We can query it at the right time and look around a certain area at a certain time and figure out things like who won the World Series in 2026, and just by looking around the position of the scoreboard at different fields and determining the scores. There's different ways we can do this. We could find a baseball, follow it around the field and see who won the game that way. We could go and read a newspaper by querying this API right at the area of a newspaper and figuring out where the ink is and reconstructing what the authors of the paper said. So there's a lot of information in this object, and so we would like to know, in subspace mechanics, we'd like to describe this field in a similar manner to the way we describe fields in kinetic theory. In other words, we describe them using distribution functions. So we're going to do the same thing in subspace. All these fields, some tensor f mu nu is going to be some sort of integral over a operator acting on our distribution function. Let's write that in a better way for you quantum mechanics people. Distribution function being operated on by some operator over some phase space. And as we get into more concrete examples, you'll see what I mean by this. But this is, again, analogous to kinetic theory of gases. Remember, in kinetic theory of gases, we have a local density as a function of space and time is defined as the integral over all velocity space from minus infinity to infinity of our distribution function integrated dvx, dvy, dvz. And so here we're producing a field based on an integral over a distribution function. We're going to do the same thing in subspace mechanics to produce our fields above here based on distribution functions and operators. And there's a nice exercise for the reader is to show that any field theory could be described in such a manner. And because there's basically infinite freedom here with our operators, our dimensions of our distribution function, it should be rather trivial to show that any difficult behaved field could be defined in such a way. I mean, we aren't even saying that f has to be smooth here, although I certainly expect that it will be. And we're going to talk about gyrons, so let's go back there. Let's take a look at our timing here. Not much information on this thing, is there? Not a sausage. 20 minutes. Okay, let's do it. We're going to go a little bit more examples just so that you're familiar with what subspace mechanics is before we dive into the descriptions of these fields. We're going to use this term from Frank Mino. And we're going to look at the simplest possible way to arrange a subspace. So if we have some distribution function for the gyrons, over some phase space, unknown phase space here. And we're going to assume that this can be written as a function over some subspace coordinate. Now this means that this is a spatial coordinate. We're visualizing it as a spatial coordinate in subspace. And then because we have a spatial coordinate, we have a time, we can also have a velocity. So we're basically treating these things like molecules in subspace, which is the simplest way to approach this, a good place to start. But we're going to give them a few more characteristics. We're going to give them an orientation, and we're going to give them an angular velocity. So this amounts to 3, 6, 9, 10, 11, 12, 13 different dimensions. So it's a 13-dimensional distribution function describing our subspace mechanics. We're going to simplify this even further by assuming we can average over the specific orientation of these gyrons. And we're going to call them, so we're going to call our distribution function a function of 3 subspace dimensions, 3 velocity space dimensions, and 3 angular velocity space dimensions and time. So now we have a 10-dimensional phase space. And this is just one way to simplify this. And we're going to say that we're going to say the following Lorentz, that we can build our electromagnetic fields, the tension and the magnetic vector potential, in the following way. We're going to say that the tension is proportional to the mean square velocity. In other words, we're going to integrate here now over 6 dimensions, from minus infinity to infinity over all of them, of v squared times f we're not going to bother with normalizing it for this intro talk, but there might be a normalization. We're just saying it's proportional in this case. And of course, we're integrating over all velocity space, all angular velocity space, all 6 dimensions. And this leaves us with a simple scalar as a function of position and time. And further, we're going to take this, these are our subspace coordinates. Eventually, we're going to convert the subspace coordinates using some function into our normal space coordinates, so that we can describe to you eventually calculate, in fact, the electric potential. And we're going to, again, following Lorentz and others, A is going to be proportional to a similar integral. I'm just going to write one integral sign, keep it simple. In this case, it's going to be a vector, the velocity. We're averaging over the velocity of our distribution function. Again, d cubed v, d cubed omega. And so we have something which in fluid mechanics you would call u, would be a bulk velocity. So this is a bulk velocity of subspace, and this is a bulk pressure, if you will. And you will see when we get to the electromagnetics lecture that these quantities satisfy Maxwell equations, And so we can reproduce electrodynamics based on our subspace mechanics, which is the goal of this lecture series. And there's a lot of loose ends you'll find here, but I hope that I've made it clear what our plan of attack is so that we can improve our understanding of fundamental physics and perhaps even build some nice, crazy sci-fi stuff, possibly even survive a little longer out here in our beautiful section of the Milky Way. So, thanks for tuning in. See you next time.